everyone, and welcome to the fourth video in the Advanced Higher Chemistry Unit 1 series. Now we're going to have a look at the magnetic quantum number. So this was one where we have this as M with a subscript L, and remember I said previously that you'll see in older documentation and questions that this might just be given the symbol M. So just be really careful with that. It means the same thing. We've just changed the notation now in Advanced Higher Chemistry. So we've said already that you have your principal quantum number that will tell us which shell you're dealing with. You then have the angular momentum quantum number, and that will tell us the shape of it. But now we are looking at the magnetic quantum number, and this tells us kind of like the direction, but also tells us the number of each type of orbital that we have. So the first shell, we have a 1s orbital, and we only have that s orbital. The second shell has 1 2s and 3p, and then the third shell has 1 3s, 3p, and 5d orbitals. Now this is dictated partly due to what we saw before. So if you have a look in the slide here, remember the shape of our s orbital is spherical. The shape of our p orbitals are these dumbbell shapes, and our d orbitals were this dz squared that had the donut in the middle, and then the other ones were like two dumbbells together, kind of like a four-leaf clover type shape. Now, the way that this works out is similar to what I just showed you with N and L. So if we have just a look back at that previous bit, so if I have N, which was my principal quantum number, so that could have been 1, 2, 3, 4, can continue, and then L, remember we said that can have a value of 0 to whatever N was minus 1. So if N is 1, 1 minus 1 is 0, so the only option for L is to be 0. 0 corresponds to an S. If I had 2, remember what I just said was that if it's to N minus 1, that can only go as far as 1, and 1 happens to correspond to a p orbital, 2 to a d, and 3 to an f. When we have a look at this magnetic quantum number, a very similar thing applies. So let's have a look at a table similar to the one that we did before of ML, because ML can have a value of minus L to positive L. Now what do I mean by that? What I mean is if L has a value of 0, then ML can also only have a value of 0, because you can't have minus 0 and positive 0. If L has a value of 1, ML could have the value of minus 1. It could also have the value of 0, or it could have the value of positive 1. If L had a value of 2, then we could have minus 2, minus 1, I don't know why I'm writing all my 1s differently, to 0, to positive 1, or to positive 2. So we're going from minus L to positive L. Okay, so minus 2 all the way through to positive 2. So it's any integer between the negative and positive L. And then when we get to 3, that could also be minus 3, minus 2, minus 1, 0, positive 1, positive 2, or positive 3. Now let's have a think about this. This is if we had an s orbital. This was if we have a p orbital. This was if we had a d orbital. And this was if we have an f orbital, which we've not really had a look at and we don't need to know too much about. Think of the shapes of these. We said that s orbitals were spherical in shape, so if we had our axes, it's just in the middle of our axes. We said there were 1, 2, 3 possibilities of a p orbital, so we could have one that was going along this axis. I don't know if you can see that, it's quite small. You could have one that's going along the y-axis, or you could have one that's going along the z-axis. There were 5 possibilities for d orbitals, weren't there? 1, 2, 3, 4, 5. So you see where we're getting at here? M subscript L, ML, is telling us which of these particular orbitals, it's telling us how many and essentially the direction. Now you are not required to match up the number, the quantum number, to the exact one. So you don't need to say, oh, minus 1 is definitely going to be px, and then this is py, and then this is pz. You don't need to do that. You just need to recognise that this dictates that there are 3 and we have our quantum numbers for that. This also tells us that there are actually 7 possibilities for our f orbitals. And that's the information you really need to know about f orbitals. We're not going to ask you to draw them. We're not going to ask you to name specific ones like we would with these, like dx squared minus y squared. So don't worry too much about the f orbitals. Just be aware that they are there, that there are 7 of them, and that these are the possibilities of the quantum number for that. Okay, so that's how this relates. So if we have a look back at the previous kind of table that we had a look at, think of the possibilities that we have just now. So n equal to 1, so in my first subshell, I only have an s orbital, so that is 1s. Here, I have 2s, I have 2p as well, but there are 3 possible orbitals in there. Each orbital can hold 2 electrons, so that's going to be 2 in my s and then 6 in my p orbital, so 8 electrons in total in my second shell. Now think of this, this is going to have 2, this now is going to be 8, we'll talk about it in a second. This has a s and my p, so that's my 8. And then we said this was d orbitals. There are 5 d orbitals, that's another 10. So that's actually 18 electrons that could be in my third shell, and so on. That's the number of electrons. Every specific orbital can hold 2 electrons. Now there's one final rule to think about, there's one final quantum number to think about when we are talking about this, and that is m subscript s. So m subscript s is telling us about the spin. So that's where our s comes in, spin. And that is only ever going to have a value of +1/2 or -1/2. And if we have a look at the slide just now, you'll see halfway down it says about something called the Pauli exclusion principle. Now you need to be aware of this, you need to know this. And the Pauli exclusion principle states that no 2 electrons can have the same 4 quantum numbers. Now let's have a think about simplest one, 1s. Okay, the first shell, so n equals 1, and so L equals 0. So I have an s orbital, there can be 2 electrons in there. If n equals 1 and L equals 0, ML, which up here can have a value of negative to positive L, well this is 0, this also has to be 0. M subscript s, there are 2 electrons in here, so this is determining which electron is which. So that could be +1/2 or -1/2. That would be like the address of my 2 different electrons. One would be 1, 0, 0, +1/2. The other electron would live at 1, 0, 0, -1/2. Okay, so they do not have the same 4 quantum numbers. 3 of them are identical and they are determined by the spin. So 1 will be spinning up and 1 will be spinning down. Okay, and that's what we can see again if we go back to the slide. That's the notation that we're seeing here. So that will determine basically between any 2 that are in the same subshell that exist in the same orbital and going in the same direction. So the px in the second shell, say there are 2 electrons potentially in there. If you have enough electrons to fill it, one will have a positive, one will have a negative spin. That will be the difference between them. Their 4 quantum numbers will not all be the same. 3 will be, but the last one will be different. One will be positive and one will be negative. This is a lot to take in for this section. So the quantum numbers are the things you really need to have a kind of grasp on. You need to understand where that comes in, but it might be made slightly clearer when I start doing things like this orbital box notation I keep sneaking in, or this 1s thing I keep sneaking in. And that is because we fill this and we have our notation as to how to actually show any atom in terms of its electron arrangement, because it's now no longer it's now no longer a way to say that lithium, its electron arrangement is 2, 1. Yeah, so we did that before. Oxygen, its electron arrangement was 2, 6. But those 6 electrons in that second shell, where do they exist? Which shells are they actually living in? So this is what we're getting away from now. So this is how it was shown to you in your National 5 data book. This is how we always dealt with it in National 5 and higher. But we're going to have a look further into that just now. So going to the slide just now, the Aufbau principle is the second principle. There are 3 that I need you to know about. So the Pauli exclusion principle told us that no 2 electrons can have the same 4 quantum numbers. The Aufbau principle tells us that the electrons fill the orbitals in order of increasing energy, which makes sense. We've always done this. We are going to fill the first shell before we move to the second shell. The only difference is the order then that we fill within that shell. We fill an s orbital before a p orbital, and we fill that p orbital before we go into the d orbital. The only slight thing is if you have a look here, so this is basically us looking at energy going from lowest energy up to highest energy in the blue up here. Now looking here, here's my 1s orbital, it's the lowest energy to fill. I then go up to my 2s orbital and then my 2p orbital, and then I break into my third shell, so 3s, then 3p, but there's a crossover here. The d orbitals are ever so slightly higher in energy than the s orbital of the next shell. So I would fill the 4s orbital before going into the 3d orbital. And then I would do the rest of the 4 shells, the 4p, but sneaking in here, I would end up with a 5s if I was going that far, but we're not going to. So an s orbital will fill before the previous shell's d orbital. And then your third rule that you need to know when we do this, I know this is confusing. The third rule, according to Hund's rule, up here, when degenerate orbitals are available, electrons fill each degenerate orbital singly and with parallel spins. Basically, you want to maximize the number of ms being plus a half or negative a half, all the same, before you go back and pair them up. So having a look here, say I've filled my p orbitals, 1, 2, and 3. I don't fill the first p orbital first. So the way I'm going to show that, like we'll go through this just now. So I'm going to say that my p orbitals are these boxes. Okay, so I've got 1, 2, and 3 boxes. So that's going to be one of my p orbitals, second and third in a shell. I'm going to come in and an electron comes in to fill it, but I have a second electron. Instead of that second electron coming in here, it's going to go into the next box. Maybe I've got a third electron that's coming into this p subshell. I want to maximize the parallel spins. Look, all of these are pointing up. They are all half-headed arrows because it is 1 electron and only 1 electron. And now, if I have a 4th electron, it's going to come in here. That's the correct notation for having 4 electrons in 3 p orbitals. Instead of the incorrect, maybe I would have said, oh, actually, I'm going to do 1, 2, 3, 4, and leave this third orbital blank. So this is if each box was an orbital. This is the incorrect way to do it. I want the maximum number of parallel spins before I come back round and pair up my electrons. For any of you who might have been in my National 5 or higher classes, say I was doing the electron arrangement for oxygen, I've always done 1, 2, and then the second shell, I've always gone 1, 2, 3, 4, 5, and 6, because I can kind of get away with doing my parallel spins and doing this kind of thing. Okay, this isn't for oxygen, this is just giving you that idea that I've done single electrons before coming back and pairing them up. Okay, so that's why I've always done it that way, because we always want individual electrons and then we come back and pair them up. And this is our Hund's rule, that we want to maximize the parallel spins before coming back to add in the electrons going in the other direction. Okay. Mass amounts of information to take in. So how do we actually represent this? Let's take lithium here as an example. Lithium has 3 electrons. So let's think about this. Let's think about my Aufbau principle and that I want to fill the orbitals from the lowest energy state. And then let's think about Hund's rule of maximum multiplicity and everything in there to try and get this together. So 3 electrons in my first shell. So if n equals 1, I only have, remember, that s orbital. So I'm going to do this as boxes just now. So that s orbital is represented by a box, and it's going to have both electrons before I move on to a different subshell. Okay, so this Hund's rule only applies when you're working within a subshell. So this is 1 because it's n equals 1. It's an s orbital, and it has 2 electrons. So 1s2, and the 2 is like a wee superscript, so it's like squared. 1s2. So there's 1, 2 of my electrons. I have 1 left over. I now have to go into, if I put the end at the side here, I need to break into the second shell, which we knew already from National 5. And that first lower energy is the s orbital. But there's only 1 electron available, so it goes here, and that becomes 2s, and this time it's a 1. Okay, that's a really messy 2, sorry, I started writing 1. So my electron arrangement is 1s2, 2s1, and that's it. That's how I know exactly where those electrons are. I'm not worried about quantum numbers just now, because this essentially shows and tells me what I need for this. 1s2, 2s1 is my electron arrangement. Now let's have a look at oxygen. Oxygen, excuse me, has 8 electrons. First shell is going to have 2 of those, and that's going to be 1s2. Second shell is going to have another 2 of those in an s orbital, 2s2, and that's what, 4 electrons in total. And then I'm going to draw out this, representing 1, 2, 3 p orbitals. I'm joining them together because they are degenerate, they have of the same energy, and this is representing my p orbitals. And what did I say? I've got 4 here, I've got 4 left over. 1, following Hund's rule, 2, 3, 4. Look, there's those 2 unpaired electrons from what I was in before. Okay, so this is in the second subshell still, because remember we said we can have p orbitals in here. They are p orbitals, and I have 1, 2, 3, 4 electrons in total, because remember, each one can hold 2. You can have a maximum of 6 electrons in here. Okay, so using the numbers like this as the electron configuration, using this here is the orbital box notation. 2 different notations, 2 new ways to represent your electrons. So let's have a look at something a bit more complicated now. Let's look at vanadium, so V. So vanadium, you would see by the data book, it gives you an electron arrangement of 2, 8, 11, and 2. Now, why do we still have these? It's interesting, and we'll see when we put this all together. So in total, this is what, 19, 20, 21, 22, 23 electrons. So let's just deal with the electron configuration first. So I'm going to go into 1s, 2. I still have enough electrons to fill 2s. I have 2p is next, and there are 6, so that's 6, 7, 8, 9, 10. I have tons left over. I then will fill my 3s orbital, and I have enough to fill that with both. 3p again comes next, and I've got more than enough because I've got 2, 4, 6, 8, 10, 12, 14, 16, 18. I still have 5 electrons left. But remember, my order, 4s is going to fill before I break into those 3d orbitals, and I only now have 3 electrons left over because I had 18, 19, 20, 21, 22, 23. This is my electron configuration. Electron configure. I cannot spell today. Configuration. Okay. Orbital box notation now. There's my 1s2. There's my 2s2. 1, 2, 3, 4, 5, 6. Then I've got 3s2. I'm going to have 1, 2, 3, 4, 5, 6. I then have 4s2.
And then the d orbitals, remember there are 5 of them in total. 1, 2, 3, oh, tight for space. 1, 2, 3. Now these are all single because I don't have enough to go back round and pair up. Okay, this is my orbital box notation. Okay, and that is my electron configuration and my orbital box notation. That's how I would go about doing that and looking at this. Now, this is the bit that I asked the question, why do we still have this? Well, let's have a look just at the first subshell for vanadium. There are 2 electrons. Let's have a look at my second subshell in total. There are 2 plus 6. Well, look, there's 8. Let's have a look now at my 3. So I've got 3s, 3p and 3d at the end here. Don't forget about that. So I've got 8, 9, 10, 11. And look, I've got 2 of my 4 shells. So this number represents the number that are in your first shell in total. This number represents the number in your second shell in total. This is your third and this is your fourth. Okay? Now, the only other thing I want to mention is the shorthand to be able to do this. So the shorthand to be able to do this would be looking at a noble gas. Now, noble gases have full shells, and sometimes, you wouldn't usually be asked that much in a question, but sometimes you would be asked to think about shortening it rather than writing all this out. Can you imagine doing this for like 36 elements, getting all the way and doing this for absolutely every single one? Now, in a question, if it asks you for the electronic configuration, it wants the full thing, unless it specifically asks you to shorten it. But vanadium, if you think by the time we get to the 4s2 and a 3d3, that is the electronic configuration of argon. So I could write argon 4s2 3d3, and that would tell me that I've got the same electronic configuration as argon plus this. Okay, that's the shortened method. So you look for the nearest noble gas that's come before it, and then you've added in the extra electrons. So that's where we are with the orbital box notation and the electronic configuration. All of this has been determined by those quantum numbers, so it's really important that you go back, you have a look at those quantum numbers and you get them settled in your head, and then you can have an understanding as to where all of this has come from. It is quite complicated, but once you work through some examples and once you start knowing that it just goes 1s2, 2s2, 2p6, 3s2, 3p6 and so on, it gets a lot easier. It becomes quite repetitive. I actually quite enjoy this part because once you get it into your head, it's quite methodical in the way to do it. So it's definitely something to have a look over, have a wee go at some questions, and I'm sure it will settle in quite well. See you later.